Have you ever wondered how your computer manages its memory resources? Well, the answer lies in a process known as memory allocation. It's a complex dance of assigning memory resources to various processes in a way that ensures efficiency, fairness, and security. Memory allocation is particularly critical in multitasking environments, where multiple processes are constantly vying for limited memory resources. Think of memory allocation as a city planner deciding where to place buildings, parks, and other facilities to make the city run smoothly. The city here is your computer's operating system, and the buildings and parks are the different processes that need memory to function. So, what are the objectives of memory allocation? First, there's efficient utilization. The goal here is to make sure memory is used effectively to support multiple processes. This is like ensuring every building in our city has a purpose and isn't just taking up space. Next, we have isolation. This is about separating process memory to prevent unauthorized access and ensure stability. Just as you wouldn't want a power plant next to a playground, you don't want processes interfering with each other's memory space. Then there's protection. Memory allocation needs to safeguard against memory-related vulnerabilities and security risks. It's the equivalent of having security measures in place to keep the city safe. Finally, performance. Memory allocation aims to minimize overhead while supporting fast memory access and process switching. It's like ensuring the city's roads and infrastructure allow for quick and easy movement. As you delve deeper into the world of memory allocation, you'll encounter different levels and strategies. Some memory is allocated statically, some dynamically, and others are automatically managed. Each approach serves a purpose, just like different types of buildings serve different functions in a city. As you can see, memory allocation is an essential part of how your computer operates. And just like city planning, it's a delicate balance of many factors that, when done right, can make everything run smoothly. Memory allocation isn't a one-size-fits-all process. There are different types, each serving a specific purpose. Let's dive into the three main types: static, dynamic, and automatic or managed allocation. First up, we have static allocation. This memory allocation is done at compile time. In other words, before the program is run, the compiler determines how much memory will be used and allocates a fixed amount for each process or variable. It's a common approach in low-level programming, making it useful for systems where memory availability is predictable and constant. However, it lacks flexibility. If your program needs more memory during its run, well, it's out of luck. Next, we have dynamic allocation. Unlike static allocation, dynamic allocation happens at runtime. The operating system allocates memory as needed, making it more flexible. If a process needs more memory, it can request it, and if it's available, the operating system will allocate it. This flexibility makes dynamic allocation a common choice in modern operating systems. However, it does require careful management to avoid memory leaks and fragmentation. Finally, there's automatic or managed allocation. In some programming languages and runtime environments, the system automatically handles memory allocation and deallocation. This can happen through a process known as garbage collection. The advantage here is that it reduces the need for manual intervention, making it easier for developers. However, automatic memory allocation can be less efficient than manual allocation, and garbage collection can lead to performance overhead. So, which type is the best? Well, it depends. Each type of memory allocation has its pros and cons, and the right choice depends on the specific needs of the system and the software running on it. Static allocation might be perfect for a simple embedded system, while a complex web server might benefit from the flexibility of dynamic allocation. And for developers who want to focus on their code without worrying about memory management, automatic allocation could be just the ticket. The type of memory allocation used can greatly affect the performance and efficiency of your computer. Just as there are different types of memory allocation, there are also different strategies for allocating memory. One of the first strategies is contiguous allocation. This is where memory is allocated in one single continuous block. It's a straightforward approach and simple to manage. However, it can lead to what we call fragmentation. Internal fragmentation happens when memory within a block goes unused, while external fragmentation refers to free memory scattered throughout, not forming a block large enough for allocation. On the other hand, we have non-contiguous allocation. Instead of one large block, memory is allocated in smaller blocks that need not be adjacent. This approach has the advantage of reducing external fragmentation. However, it does require additional data structures to manage the allocation, making it a bit more complex. Moving on, we have fixed and variable partitioning. In fixed partitioning, memory is divided into fixed-size regions, with each partition assigned to a process. This approach is pretty simple, but it can cause internal fragmentation, as all partitions may not be fully utilized. Variable partitioning, on the other hand, offers more flexibility. Partitions are of varying sizes, fitting the process needs more accurately. However, it requires careful management to prevent external fragmentation. Next, we have paging, a strategy that helps reduce fragmentation and supports virtual memory. In paging, memory is divided into fixed-size pages. Virtual addresses are then mapped to these physical pages using page tables, providing an efficient allocation method. Then there's segmentation, where memory is divided into logical segments representing different parts of a program, such as functions or data. This approach provides a logical structure to memory allocation, but like others, it can also lead to external fragmentation. And lastly, we have the buddy system. Here, memory is divided into blocks of sizes that are powers of 2. The beauty of this system is that it allows efficient merging and splitting of memory blocks. It's a strategy that's often used in kernel memory allocation, where the dynamic allocation needs can be quite diverse. So you see, each strategy has its benefits and drawbacks. Contiguous allocation is straightforward, but can lead to fragmentation. Non-contiguous allocation reduces external fragmentation, but is more complex. Fixed partitioning is simple but can lead to wasted memory, while variable partitioning requires careful management. Paging reduces fragmentation and supports virtual memory, but it needs an additional layer of address translation. Segmentation provides logical structure, but can lead to external fragmentation. And the buddy system, while efficient, requires memory blocks of specific sizes. The strategy used for memory allocation can make a significant difference in how effectively a computer uses its memory resources. In the end, it's all about finding the right balance and using the strategy that best suits your specific needs. So why does all this matter? Why should you care about memory allocation? Well, let's take a moment to distill everything we've discussed. Memory allocation is not just some obscure technical jargon. It's a fundamental mechanism that powers the digital world as we know it. It's the invisible hand that guides the operations of your devices, from your desktop computer to your smartphone, and even the servers that host your favorite websites. We've talked about the different types of memory allocation: static, dynamic, and automatic. Each has its own strengths and weaknesses, and the choice between them often depends on the specific needs of the system and the software running on it. We've also explored the various strategies for memory allocation: contiguous allocation, non-contiguous allocation, fixed and variable partitioning, paging, segmentation, and the buddy system. They all provide unique approaches to managing memory in an efficient and effective way. But why is this important? Well, efficient memory allocation allows for better performance of your applications and overall system. It ensures that memory resources are utilized effectively, reducing waste and increasing speed. It also plays a vital role in isolating processes, protecting your system from potential vulnerabilities and security risks. Moreover, understanding memory allocation can help you write better, more efficient code. It can help you troubleshoot and optimize your applications, making them faster and more reliable. It can also give you a deeper understanding of how software interacts with hardware, bridging the gap between the physical and the virtual. But perhaps most importantly, appreciating the intricacies of memory allocation can help you gain a deeper respect for the complexity and elegance of modern computing systems. It can make you realize that every line of code, every process, every byte of memory is part of a larger, intricate dance that keeps our digital world spinning. So the next time you fire up your computer, take a moment to appreciate the intricate ballet of memory allocation happening behind the scenes. Understanding memory allocation can give you a deeper appreciation for the complex processes that keep your computer running smoothly. Remember, every byte counts.